Okay, thank you for the invitation. So Félix did the hard part. I will do the easy part. And from my lack of preciseness, you will realize that probably Félix and Julie, like in that matter, maybe did most of the work. I will try my best. Okay, so I will mostly talk about two applications. One which is related to a variation of branching Brownian motion, a standard model by Berestiki and Schweinsberg, and which has been mainly studied by Julie Tournière during her PhD thesis with Pascal Maillard, and some extensions that we did together using those spinal decomposition to prove some results. And the second part, which was the original motivation of what Félix presented, which is a model that we originally investigated in a slightly more complex setting, taking population saturation into effect during Veronica during her PhD thesis, which is a model of which is a branching process with recombinations that I will introduce at the end. Okay, so the first part of my talk, again, so it's like a branching Brownian motion with inhomogeneous branching rates. So first of all, let me give you some motivation for studying such an object. So the motivation is a more complex model, which has been introduced in 2018 by Birzu and Alacek and co-authors, which is a noisy FKPP equation with demographic noise. Okay, so what you see here is the usual FKPP equation, but you have some extra flavor, which is given by this white noise, and also an alley effect, right? Which corresponds to the fact that at least when B is large enough, then the reaction term will be optimized at intermediary frequency. So typically, the optimum for the reaction term, if you have a traveling wave solution, which is the case, will occur not at the tip of the front, but in the bulk. Okay. So you will think at first sight that this alley effect does not make such a big difference, but actually it does, and it does quite a lot. And so recent simulation and studied by Birzu and Alacek in a very nice PNS paper investigated the effect of demographic fluctuation on the front. So typically what they did is that they looked at the typical time it takes to observe a fluctuation of order n. Okay. And what they observe is like a phase transition. So first of all, when B is small enough between 0 and 2, so B is equal to 0 corresponds to no alley effect at all. So this corresponds to the usual FKPP equation. Then in order to see a fluctuation of order n, you need to wait for a time of order log n to the power 3, right? So to speak, like the effective population size at the front is not given by capital N, but it's given by log n to the power 3. Okay. So interestingly enough, if you increase the value of B, okay, and now you're like in between 2 and 4, then the effective population size will not be logarithmic. It will be n to the power alpha minus 1. Okay. And so you expect, if you look at the genealogy, not to see Bolthausen-Schnittmann as here, but to see something like a lambda coalescence of the type beta alpha 2 minus alpha. I always forget about the parameter. I think this is in the right order, but okay. And then if you push even beyond that point, so if you take B greater than 4, so a huge alley effect, then now the effective population size will be of the order n. Okay, so you start from the FKPP with demographic noise, you add the alley effect. At the beginning, when B is equal to 0, you see Bolthausen-Schnittmann, okay? Then when you increase the value of B, you enter like the lambda coalescent world with like a lambda equal to having the beta distribution. And when B is greater than 4, then you see Kingman, okay? So what's quite kind of intriguing about this model is that, you know, I mean, easy to define, but as far as I know, there are very few rigorous results about it. And the only one I know is a very nice work by Etheridge and Pennington, where they prove that in a certain region of this parameter space, not B greater than 4, but in some sub-region of this domain, they could prove convergence of the genealogy to the Kingman coalescence. Okay, so I stated in a loose way, but so somehow what they do is that they kind of sample K particles at the tip of the front. They look at the genealogy. And under the right time scales, they prove convergence to the Kingman coalescence. Okay, but this is a very technical proof. It takes 90 pages. It's very clever, of course. And I mean, and this part of the region here is completely unknown. I mean, from a rigorous point of view, there are some like heuristic arguments in the paper of Birzu and Alacek, but I mean, this is beyond my intelligence, I think. I mean, it's very difficult to guess what's going on. I mean, they get the right answer, but as a probabilist, it's kind of difficult to relate to their arguments. Okay, so now let me present you a toy model for studying this model, which was the model studied by Julie Tournière in her PhD thesis. And so what she proposed is to simplify the problem by introducing a system of branching Brownian motion with inhomogeneous branching rate. And the way it works, it goes like this. So you have two parameters. One is mu, which is strictly positive, and the other one is rho, which corresponds to a branching rate. Okay? Rho should not be between 0 and 1. It should be greater than 1. I'm sorry, greater than 1. And so you have your system of Brownian particle on R+, and you have a drift minus mu, exactly as in Beresicki and Schweinsberg. And the particles are killed at 0, right? So if you take a typical particle, then on a time scale of order 1, this particle will actually be killed. Okay? And then you have an inhomogeneous branch rate, and this is kind of like the twist compared to the original model of Beresicki, and Schweinsberg. So when x is greater than 1, you branch at a rate a half, but close to the killing boundary, when x is in between 0 and 1, you have a branching rate which is slightly higher, rho divided by 2. Okay, so it's exactly the same model as Beresicki, and Schweinsberg, except that close to the boundary, you have an excess in the branching rate. Okay, and I mean, what I find very surprising here is that it seems like a very mild modification, but you will see that at the end, it makes a huge difference. Okay. So what is the motivation behind this? Well, you can see rho as a parametrization of the Ali effect. If you assume that rho is greater than 1 and not rho in between 0 and 1, and you think of your cloud of particle as a description of the front of your particle system, then when rho is greater than 1, this is telling you that somehow the branching rate is higher in the bulk than in the front of the cloud of particle. Okay, and this minus mu here will correspond to the speed of the front. So rho is equal to 1. Again, it's like the standard branching Brownian motion particle by Beresicki, and Schweinsberg. Okay, so we have a two-parameter model. And now what I would like to do is to reduce the dimension of the parameter to 1 by choosing mu in such a way that roughly, on average, the number of particles remain constant. Okay, and the idea behind this is that, again, what I would like to have is a toy model for a stable front. Okay, and if I want to have a stable front, well, I don't want to have the number of particles to increase exponentially or to decrease exponentially. So how to choose mu as a function of rho to maintain the number of particles constant? Well, the first idea is to use the many-to-one lemma. So the many-to-one lemma is telling you that if you want to compute the expected value of some additive function of your system of particles with respect to some test function f, then this is exactly the same thing as integrating your test function over the density of particles. Okay? And here P is the density of particle at y at time t starting from a single particle at position x. And Pt of xy as a function of y and t will be solution of the following fundamental equation. Okay, and so if you look at the right-hand side here, you have a differential operator. So the second derivative here corresponds to the diffusion of the particle. The transport term mu corresponds to particles going with a drift minus mu, because in transport, like the drift gets a negative term, to 0. And R of x, okay, is the inhomogeneous branching rate. So at position x, you produce new particle at a rate R divided by x. And finally, you have this Dirichlet boundary condition, which is telling you that when a particle hits 0, then it's dead. Okay? So now, having this equation, the aim, again, is to choose mu in order to keep the number of particles under control. okay, in order to have like a time order. Yes.
Now you just think the equation for any value of rho, like rho could be 1.
Yeah, it's very general. Actually, R could be anything you want, right? So here I choose it as a step function, but because so R of x here it's a step function, right? So it's rho divided by 2 and 0, 1.
Yes.
And then it's 1 plus infinity, but actually this many to 1 lemma is much more general than this. Okay. Okay, so now, so the idea, of course, is to do some spectral decomposition. If you look at the right-hand side, you get a differential operator, and if you think of it as a big Perron-Frobenius matrix, then the large time behavior of the solution of this fundamental equation will be driven by the leading eigenvalue of this linear operator. And so the idea here is to do some spectral decomposition in order to compute the leading value of this linear operator. Okay, so that's the idea. Okay, so first thing first, so you see that in some ways, like the problem is somehow ill-posed because I set some boundary condition at 0, but I need somehow to specify what happens at plus infinity. Okay. So one way to do that is to take a very large space horizon, L, that will eventually go to plus infinity. I take exactly the same equation, but now instead of killing particles at 0, I also kill the particle at L. And if I take large enough, I hope that at the end, this will not make such a big difference. Okay? So you get this differential operator on a bounded domain, bounded but large. And now you would like to investigate the spectral decomposition of this operator. And well, okay, so this operator is not self-adjoint because of the drift here. But actually, I mean, there is a very natural way of making it self-adjoint by some kind of Girsanov transformation. So you set P equal to a Girsanov term here multiplied by Q. Okay, so this corresponds really to a Girsanov transformation when you get rid of the drift in this part of the differential operator. And it's a direct computation to show that if P is solution of this equation, then Q must be solution of this equation here. And the nice thing about this transformation, of course, is that you started with something which was not self-adjoint, you do the Girsanov transformation, and you end up with a self-adjoint operator on a bounded domain with Dirichlet boundary conditions. And okay, so now you're self-adjoint, so which means that well, you're in business, right? You can apply the standard like Sturm-Liouville theory, which is telling you that the eigenvalue of the operator can be numbered from the greatest to the lowest. So there is one greatest eigenvalue for your operator. You have an L2 decomposition, so Q can be written in the following way. Okay. So now what you have to remind yourself is that what we are interested in is not Q itself, but it's P multiplied by this Girsanov transformation here, okay? And so if you admit that when T is going to plus infinity, everything will be washed away except for the first terms that will be dominant in the spectral decomposition, which will be dominant with respect to the other, then P is this term Q here, this Girsanov term here, multiplied by the first term in my L2 decomposition, okay? And so now comes the important part. You see that when you look at the exponential expansion of this solution P, there are two terms. One, which is coming from the spectral decomposition, so there is this lambda 1L, and one which comes from the Girsanov transformation. And so if you remind yourself that what we want is to keep the number of particles under control, neither an exponential or an exponential growth or an exponential decline, then you need simply to take mu in such a way that 1 minus mu square 1/2 plus the limit of this when L is going to plus infinity will be equal to 0. Okay? Okay, so what Julie proved in her PhD thesis is that when you let L go to plus infinity, everything works nicely. So in particular, if you look at the behavior of this leading eigenvalue, then lambda 1L is going to a limiting value lambda 1 infinity. And now comes the interesting part of the story. again, you will think that adding just a small inhomogeneity close to 0 will not make any difference, but actually it does, right? So what he showed is that there is a critical value, rho 1, okay, which is strictly positive, such that when rho is in between 1 and rho 1, which corresponds to a weak allie effect, then lambda 1 infinity is equal to 0, okay? And when rho is greater than rho 1, then you have, so this corresponds to a strong allie effect, then lambda 1 starts increasing and becomes strictly positive, okay? So to keep the number of particle constant, again, what we need to take mu in such a way that this guy plus this guy is equal to 0. So you get mu, so the speed of the cloud of particle, which will be equal to square root of 1 plus 2 times lambda 1 infinity. Okay, so in particular, you already see a phase transition in the sense that if rho is in between 1 and rho 1, mu is always equal to 1. Okay, so the speed of your cloud of particle does not change. But when you go above this critical value, then mu starts increasing with lambda 1. Okay, so you see no change in between 1 and rho 1. And then suddenly, after this critical value rho 1, your system of particles start moving faster. Okay, so relation to previous work. So I already mentioned this several times, but if you take rho is equal to 1, then this corresponds exactly to the standard model of Beresicki, and Schweinsberg. And it's now a celebrated result that if you take the population size, then after proper space and time scaling, then this converges to an overbranching process, okay? And the genealogy converges to the Bolton-Sneedman coalescence, okay? And so one conjecture, like in Julie PhD thesis, so this is an open problem, is that if you are like below rho 1, then you should see exactly the same behavior, okay? So convergence to the never branching process, and the genealogy should converge to Bolton and Sneedman. Okay.
For any value between 0 and 1,
no, so rho has to be greater than 1. Okay, so it's in between rho and rho 1. You should have exactly the same scaling limits as the one of Beresicki, and Schweinsberg. Okay. Okay, so back to my PDE here. So this corresponds to this case. Okay. And so now if we believe that this is a nice toy model to kind of reflect the qualitative behavior of this PDE, then for rho greater than rho 1, so when mu starts increasing and lambda 1 becomes positive, then somehow we should observe also this phase transition. Okay, so from lambda from beta coalescent to the Kingman coalescent. Okay, so so let's look at what happens when rho is greater than rho 1. So when rho is greater than rho 1, so I hope so there is this weird function at first that I hope I will be able to explain that will become less mysterious in the next few slides. But the phase transition is directly related to the sign of this function. Okay, so phi of rho. So phi of rho is mu of rho minus 3 beta of rho. So first of all, you see that when rho is is smaller than rho 1, then mu is equal to 1, and beta, so beta is square root of 2 lambda 1. So it's 0, basically. So when rho is below rho 1, below the critical value, phi is equal to 1. Okay, it's equal to 1. Then it's not very difficult to convince yourself. I mean, you have explicit expression for all those quantities as a function of rho. And looking at this computation, you can easily convince yourself that this function, when you go beyond this critical value, starts decreasing. Okay, so it's at 1, it's flat at 1, from 0 to rho 1, and then it starts decreasing, and you can find a value rho 2 such that this function is equal to 0. Okay. And this is where the phase transition will occur. So what Julie proved, and I think this is, I mean, for me, it's really an amazing result, actually, like that if you take rho in between rho 1 and rho 2, okay, then the population size converges to an alpha stable CSBP. And this corresponds exactly to what's called the semi-push regime that I was describing in my first slide. Okay? And so in this talk, what I would like to convince you is that now, if you take rho greater than rho 2, namely when this function, this mu minus 3 beta that you have to keep in mind, becomes negative, then what you see is a failure process. And when you look at the genealogy, you see the genealogy of a critical branching process, which is exactly this Brownian CPP that Felix was describing in the first part of the talk. Okay, so in the remaining of the talk, I will give you, some intuition of why you see this transition, why this quantity is so important. And I will try to convince you that when this guy becomes negative, then you should converge to a failure process with the genealogy at a given time that will correspond to a Brownian CPP. Okay. Okay, so back to spectral theory, because everything comes from here, actually. Okay, so first, what you have to remember from my previous slides is that when L, this like a spatial boundary condition, is going to plus infinity, you go to a limit which is strictly positive and which is increasing in rho. Okay, so first fact. And the second fact is the following. You can compute explicitly the eigenfunction corresponding to lambda 1 as a function of L. Okay. There is an ugly expression of this eigenfunction between 0 and 1. Okay, I spare you with this, but you can actually compute it, and it does not depend on L, which is nice. And when y is greater than 1, so in between 1 and L, this is an hyperbolic sign of this form. Again, this looks like a complicated expression. What you have to remind yourself, the only information you need here, and again, everything is completely explicit, right? You just compute and you find this. What you have to remind yourself is the following. When you take L going to plus infinity, okay, then this V1 decreases exponentially at a rate which is directly given by beta, okay? So the rate at which the eigenfunction decreases is directly related to the leading eigenvalue of your operator, okay? And so you decrease at a speed which is given by minus beta. Okay. So now I would like to go back to what Felix was describing in the first part of the talk. So what I would like to do is to compute the moment of my trees at a certain large time horizon. And for that, I will use like a spinal decomposition, a many-to-few lemma, okay? And the first building block of this many-to-few lemma is the one spine, okay? So how do you construct the one spine? Well, you need a harmonic function, okay? So so this is the continuous time and continuous space setting, but it works exactly the same way. So you will say that a certain function h is positive harmonic if the following additive functional, and this is something that Felix mentioned in the first part of his talk, is the following additive functional is an additive martingale. Okay, so h will be harmonic if this is a martingale. So now by the many-to-one lemma, the expected value of this martingale is equal to h integrated over the density function of your particle system, where P, again, is the solution of this partial differential equation that I referred to at the beginning of my talk. Okay, so you want this guy to be a martingale. So if you want it to be a martingale, then you need the derivative of this guy with respect to time to be equal to 0. So you take the derivative with respect to time. You end up with the derivative of the density function. You can replace the derivative with respect to time by the differential operator L. That was, this one, okay? And you do an integration by parts. And what you end up with is integrating the density function over the dual operator applied on the function h, right? So because you do the integration by part, then the plus mu is replaced by a minus mu. Okay, so you need h to satisfy this. So if MT is an additive martingale, you need h to be the solution of the following Dirichlet problem with, of the following Dirichlet problem with zero boundary condition at 0 and L. Okay. So now it's a computation, but you can check that if you take h of x, so of course, I mean, exactly. So if you remember Félix talk, like in the multi-type branching case, I mean, this works exactly the same way. So if you want to construct an additive martingale in a multi-type branching process, you take the right eigenvalue of the mean matrix. So you want to think of this dual operator as being the mean matrix is in infinite dimension, okay? And of course, a way to construct an additive martingale is to take h equal to something which is related to the right eigenfunction of this operator, so v1 infinity. Okay, so h equal to v1 infinity exponential of mu x, and you can multiply it by any constant you want, okay, will be a harmonic function for your particle system. And in the matter, I could choose C as I want, as long as it's positive, and I will choose it to be this constant. I mean, you will see why it pops up in the next slide. Yeah. Okay, so I have my harmonic function, and so now I have my dual operator. I can construct the Dubage transform in order to get my one-spine process, and the resulting process, okay, will be this guy. Okay, so if you want to get some intuition of what's going on here, what you have to remember is that if you take a typical particle in your system at the beginning with no conditioning, then it's a Brownian motion with a drift minus mu. Okay, so now when you do the Dubage transform, this exponential of mu x gets rid of the drift minus mu. It cancels it, and it replaces the drift by this weird-looking term, v1 prime divided by v1. So now you want to think of the one spine not of a typical particle, but a particle which is somehow conditioned to survive up to infinity. And so what you see is that as the denominator, there is something very important here, is that this v1 is actually equal to 0 at 0, which means that when your spine is getting close to the killing boundary, then you get this infinite drift that pushes you away from 0 and makes you survive. Okay, so replacing minus mu by this guy somehow condition your particle on surviving forever. Okay, so you get the first building block of your one spine decomposition, and now comes the important part. Okay, so you can compute the invariant measure of this one-dimensional diffusion. I mean, there is an explicit expression for this. And the invariant distribution is actually something very simple. It's v1 squared dx. v1 squared dx. Okay? And so now if you remember what kind of makes the phase transition in the pushed regime, everything depending on the sign of this guy. So if this is positive, this is semi-pushed. So you will get alpha stable CSBP. If this is negative, okay, then you will get the failure diffusion. So how does it pop out? It pops out exactly here, because if you look at this expression, if I look at the expected value of h of the spine at equilibrium, I get h of x integrated over the invariant measure. Sorry, that should be pi of x. And now h of x is exponential mu x v1. And so you get exponential mu x v1 to the power 3 dx. Okay. And now if you remember that v1 has an exponential tail with a rate of decrease which is equal to beta, then here, like at infinity, you get an exponential of mu minus 3 beta times x. Okay. Which means that h of x at equilibrium is integrable if and only if mu minus 3 beta is negative. Otherwise, it's not integrable. You have an invariant measure, but when you integrate the harmonic function of the spine at equilibrium, this becomes infinite. Okay. So now, okay, so that's just a computation, but how does it relate to the spinal decompositions that Félix showed you like in his talk? Well, it goes like this, right? So what you have to remember again, it's not exactly the same notation, but more or less, I hope. So what we want to compute is the chaos moment of the tree. Okay, so again, what we do is that we take the sum of every k applets, okay, of a certain functional of the distance matrix of your sample points. So this is this distance matrix and the types at the leaves. Okay. And now the many-to-few lemma is telling you that this expression, which involves a lot of terms, can be reduced to something much simpler, which is just the uniform CPP. So actually the uniform CPP is nothing else than the uniform ultrametric tree with k leaves. Okay. But this simplicity, so the cost of going to something very complicated with a lot of terms to something much simpler with only k leaves comes at a cost. And the cost is this radon-nicotine term that you have to control. Okay. So just to refresh your memory, so this Q that you get on the right-hand side is the k-spines process. So again, very simple. You first generate a uniform ultrametric tree with k leaves, simplest object you can think of. Okay. And then once you have your genealogy, you run independent one spine along the branches of your tree. Okay. And then you have to trust me on this, but this is the analog of Félix formula before. In the continuous space-time setting, your delta k is given by the following formula. So it's a certain functional of your spine at the branching points and your spine at the leaf points. Okay. So again, this radon-nicotine term delta k is telling you. So the way I think myself about it is you think about the uniform CPP as an ansatz. You say that should be my limiting genealogy because I expect to see something which looks like a branching process. I put this ansatz, and of course, when I put this ansatz, at least before going to infinity, I know that I did a mistake, and the way I correct the mistake is by adding this delta k term here. And in general, when T is fixed, I mean, this is kind of an ugly correction because there is a lot of correlations between the different branching points. Because if I tell you, well, at the first branching point, my spine was at this location, then this is telling me something about the location of my system of particles at the second branching point. Okay, and so the way you do the correction at finite T, well, it's not so nice, right? Okay, so fine. But now the claim is that when T is going to plus infinity, and this is exactly what Félix showed, like in the multi-type branching process setting, is that actually this delta k completely decorrelates from the genealogy. So why is that? Well, because, and this is exactly the argument that Félix spelled out in the first part of the talk. If you take a uniform CPP on 0T with T very large, if you take a typical configuration of the CPP, then the distance between two branching points, or like between a branching point and a leaf, it's of the order it's of the order T, right? And so if you believe that your spine process has some nice mixing property, then everything occurs as if you were just forgetting about all correlations and you were just at every branching point and at every leaf point, you were just assigning IID random variables which are sampled according to the invariant measure of your spine. Okay? And so of course, this makes things much easier because at the limit, what you expect is that the expected value of this ugly product becomes actually a product of expected value. So you will get mainly two terms. So first of all, you will have this term, so the expected value of this term to the power k, evaluated at the invariant distribution of the spine. And this will be exactly this lambda k minus 1 term, where here you see that this, no, it's not lambda, it's sigma. Where this term is just exactly this quantity, but evaluated at the invariant measure of the spine. Okay, and because you are like in the fully pushed regime, mu minus 3 beta being negative, you know that this will be infinite, and this is where like things pop out. Okay. So normally in my formula there is something missing. You should get the expected value of this guy to the power k. Okay. But I choose exactly the constant c in such a way that this term is equal to 1. Okay, so you can there is one extra degree of freedom here in the choice of c, such that when you take the expected value of this guy to the power k, then this is exactly equal to 1. Okay, so again, you want to see this as the expected value of a product that splits into two parts. And the first part, so the expected value of this delta k, because of my choice for the renormalization constant, become lambda to the power k minus 1. Okay, so it's just a constant at the end to the power k minus 1. Okay, so you need some extra ingredients, namely Kolmogorov type of estimate. You can think of it as a zeroth moment of your tree. And so what we can prove with Julie is that in the fully pushed regime, where mu minus 3 beta is negative, then the probability of survival behaves as in a usual Galton-Watson process. Namely, you have a decrease in 1/t times a constant, which is again related to this very important quantity here. And then you put everything together. So what you want is the moment of your tree conditional on survival. So you want to rewrite the previous approximation in such a way that the probability of survival pop up. So here you had like a lambda k minus 1. This becomes a lambda to the power k divided by lambda, and this guy is the probability of survival. Again, as this is very important, this is finite. So that the probability, so that the kth moment of your tree now is given by the following expression. So if you forget about this, about like the genealogical term in this spinal decomposition, then exactly as in the multi-type case, what you get is lambda to the power k factorial, which corresponds to the moment of an exponential random variable with parameter lambda. So this kind of indicates that what you will get at the limit is a Yaglom type of law, namely the size of your population conditional on survival will be exponential with this parameter. You do a renormalization by 1/t for the population size and the time of coalescence, and you get a result which is very similar to the ones that Félix presented, namely that conditional on survival up to time tn, you have convergence of your sequence of ultrametric spaces to a continuum object, and this continuum object is just the Brownian coalescent point process decorated with the invariant measure of your spine process. Okay, so if this still looks like a bit intricated, let me tell you what each coordinate is more or less telling you. So the convergence of the first coordinate is telling you that you have a Yaglom law. You converge to an exponential random variable at the end of the day, right? Once properly rescaled. The second coordinate is telling you that when you look at the genealogy, you have the genealogy of a critical branching process, which is just the Brownian CPP of Popovich. And the third coordinate is telling you that you have propagation of chaos, namely that if I sample k guys uniformly at random, I get a k IID random variable, which will be distributed according to the spine measure. Okay, so that's what this. So this convergence statement contains actually a lot of information, right? So about the genealogy, about the size of your population, and about how like types are kind of scattered. Types are positioned here on the real line, are scattered along the real line. How much time do I have? Like 8 minutes. Okay. Yeah, some related work and perspectives. So of course, we are not the first one to look at such problems. So first, there is a very nice article of Ellen Powell in 2015. And what she does is that she considers branching Brownian motion in a bounded domain of RD. So it's very general. It has no drift in the sense that if you look at the generator, it's directly self-adjoint, so it's slightly different. And what she proves is something of the same flavor, namely that you have convergence, you have a Yaglom law type of limit. And you also have convergence of the genealogy to the CRT, right? And this is exactly the questions that Anton was asking at the beginning. What she does is, I mean, she uses a very different set of techniques to prove something which topologically is quite different. She kind of defines the contour process of a branching particle system. And what she managed to do is to relate this, I mean, this is kind of a complicated object, to the contour process that you should get at the end, namely a Brownian excursion. Okay. There is a more recent result by Cipriano, Orton, and Roberts that we learned about it quite recently. And so what they do is that they actually also consider moments of branching processes, but with no mention of genealogies. They just look at the moments of the population size. And they make a very important assumption. They make the assumption that, so in a way, it's a very nice paper. I mean, I don't want to undermine the paper by, it's very, very general. So they talk about very general branching processes and so on, but also they make very strong assumptions. So the first one is that H is bounded, which is not our case here, and I will go back to this in a second. And they also assume that you have Perron-Frobenius type of property for the one-spine process, that you converge to the equilibrium exponentially fast and so on. Okay, and so under those assumptions, they managed to prove that the population size is also converging to an exponential random variable, so you have the Yaglom law at the end. Okay. So in our case, and I think this is a very important difference, we assume that H, I mean, we are like in a case where H infinity is equal to infinity. And I think this really goes beyond technicality, because if you think about it, I mean, if you're kind of convinced by the argument I gave you before, you see that this transition between semi-pushed, what Julie has studied during her PhD thesis, and the pushed case, the fully pushed case, is really due to the fact that H infinity is equal to infinity. Why is that? Well, because the semi-pushed and the pushed case is really delimited by the fact that H at equilibrium of the spine is integrable or not, right? It's because H has an infinite subnorm that you get those two regimes. If you don't have this property, actually, you cannot see this phase transition. So yes, so everything is really related to this, right? And of course, if this is the invariant measure, if you assume that H is bounded, then automatically this condition is fulfilled. Okay, so of course this begs the natural question, and this is something that Felix mentioned during his talk. Can you do some spinal decomposition in the semi-push regime? And we believe that this is the case, but now that some cutoff is needed, and I mean, this type of cutoff is actually quite standard. This is what has been done in the original paper of Berestiki and Schweinsberg, and also in the paper of Julie Tournière. And I think what we want to advocate with this method, I mean, what I really like about it is that you want to resolve a problem about trees, and about like trying to get some limiting law for the genealogy of your tree, and you rephrase this question in terms of stochastic processes, right? The genealogy is settled. It's just like the uniform CPP. It's the simplest object you can think of, and now you run some diffusion on it, and the game is to try to find some property of those diffusion when they run along the branches of the tree. Okay, so starting from a tree problem, of course, I mean, this is nothing new. I mean, this is why like those spinal methods are so powerful. You start with a question about tree and you rephrase those questions about stochastic processes. And what I feel is that somehow those kind of methods could give you kind of like a very like kind of, there is a very general methodology that allows you to go from one to the other, just not by one-dimensional spinal decomposition, but for k-dimensional decompositions. And so what remains, of course, is going beyond the toy model. And I already mentioned that this was already addressed by Alison Etheridge and Sarah Pennington. For a certain like range of the parameter space, but there is still a lot of questions remaining, of course. Okay, so I guess I have 2 minutes to present the other model, which, yeah, maybe I stop here.